Now, today we'll be looking at connection design and in particular Rivet connection design. So before we go into the design process, a few things need to be understood. One is that what are the connections requirements that we need to do, and what are the basic concepts behind the connections. So now, few things I would like to highlight here. Number one is that we are designing it to the limit state. So the average of the factored force and the connection and the force effect in the member at the same point is what is calculated. And at least 75% of that force effects in that member. So this 75% of the force effect in the member is essential. Now the end connections for diaphragms, cross frames, lateral bracing, and other members are all factored member loads because we are following the limit state, and as per the limit state we consider till the plastic stage of the element, and therefore we give it a factor of load. Similarly for bolt connections here, they should be symmetrical about the member axis so that the distribution of loads is equal towards the bolts and the welds. Now coming to rivet connections. Now since rivets are generally fixed or permanent fixtures, which means unlike bolts, you cannot change them or open the bolt and remove it out. We are very much concerned with the strength of the joint that we are going to provide. Now, we are considering four major types of failure paths of the joint here. Number one is the tearing of the plate. As can be seen in this diagram, under tension at that particular point here, when there is a force applied along both sides here and here, the member undergoes tearing in this case, and therefore we need to be able to design the load, the plate for this particular tension failure happening here. And therefore the formula as per the code here is P1 is ST into P minus D into T. ST is the allowable tensile stress of the plate material. P is the pitch, that is the distance between two rivets, the horizontal distance between two rivets. D is the diameter of the rivet hole, and T is the thickness of the plate. Now it is to be noted here that while we are doing the allowable tensile stress of the plate material, the materials that we are going to connect should be of similar thickness when two plates are connected to each other, because it makes it easier to do the load distribution and much of the load is now easily transferred. Now going on to the next process, method of failure is the shearing of the rivet. Now whenever there is a pull, if the plate does not fail, then the rivet is going to take that load and fail. And therefore you have a formula given here, which is SS being the allowable shear stress of the rivet multiplied by the area of the rivet. Now that is pi by 4d square, right? As seen in the previous type, it was ST the allowable tensile stress of the plate material, whereas here we are looking at the allowable shear stress of the rivet material. The third procedure we're looking here is the crushing of the rivet. When the load that is applied onto a rivet is so large that when the surface between the rivet and the plate gets damaged or gets pulled, it's very much similar to just inserting, having a pen go through a piece of paper, and then when you pull it out, neither the pen or the paper undergoes shear or tensile stress. In fact, it is just that the paper now gets a bigger hole diameter than it previously was. And therefore, here we are looking at the allowable bearing stress between the rivet and plate material multiplied by the diameter of the rivet and thickness of the plate. This is a very simple connection of the contact stress that we calculate here. The fourth type is the tearing of the plate at edge. Now, in some cases, it may happen that the plate from the edge, when applied by forces, will undergo a tearing at this particular point here. And therefore, if the margin is too small, it may fail here. And therefore, because this happens generally when the distance between, or the gauge distance or the end distance between the rivet and the end of the plate is not matching the minimum, and therefore a minimum margin of 1.5 times the diameter of the rivet is usually provided to prevent this sort of failure of the plate at the edge. Now, going forward, we'll also be looking at, apart from the various failure types, it can also be the efficiency of the rivet is essential. And therefore, we are going to consider the minimum of the three failures that we have seen, of the four failures that we have seen. The last failure, which is the tearing of the plate, is not really considered here. The reason being, it can be eliminated if the spacing is given properly. And therefore, this efficiency considers the minimum of the three forces, three failure types, divided by the thickness, the shearing stress multiplied by the P, the pitch, and T, the thickness of the plate. Apart from that, the allowable outside load the plate does not tear in the second row can be given by this formula, whereas the P4 is the tearing failure that we have seen can be given by this method, which is St into P minus D multiplied by T plus the minimum of the second and third failure type. So the second and third failure here was the shearing of the rivet, given here P2 is SS into pi by 4D square, and the crushing of the rivet, given by this formula, P3 is SC into dt, and therefore that is the formula. Now, looking at the design of rivet, first thing we are going to follow is the diameter of the hole required. So if the thickness of the plate is more than 8 millimeters, we follow the Unwin's formula, which is D is 6 times the square root of T. Otherwise, you can obtain the same diameter by equating the crushing strength to the shear strength in a double riveted zigzag joint, which means SCT is pi by 4 DSS. Only valid for the thickness being less than 8 millimeters. However, the diameter should not be less than T in any case. The diameter is tabulated under IS 1928-1961. Pitch is designed by equating the tear strength of the plate to the shear strength. This takes the following form: St into P minus dt is equal to SS into 2 pi by 4d square. Now remember, this formula was defined as one of the failure modes, and this is the second failure mode. But the pitch should always be greater than equal to 2 times the diameter to accommodate heads of the rivets, because Apart from the diameter of the rivet as it is, the head of the rivet should also be accommodated. Therefore, it should not clash or cause inconvenience in design here. The margin, we gave the margin very important for the fourth type of failure, which was the tear failure, as 1.5 diameter, 1.5 times the diameter. And in order to design boiler joints, we should also comply with the various other Indian boiler requirements not necessarily covered here.